In many enterprise IT environments, target systems like Active Directory, SAP, and AWS operate as isolated silos with no native communication between them. IdentityIQ acts as a centralized orchestrator, providing a programmatic bridge between these disparate endpoints. The platform functions by mapping account data from these disconnected systems into a unified internal registry. This is the IdentityIQ high-level architecture diagram. To understand how the platform actually operates, we have to look past the presentation tier and the user interface. Instead, we need to focus entirely on the application tier, specifically the Apache Tomcat container. Operating and troubleshooting IIQ requires understanding exactly how this application layer processes, serializes, and correlates identity data at scale. At its core, IdentityIQ is a heavy-duty Java web application, packaged and deployed as a standard IdentityIQ.war file. This WAR file requires Apache Tomcat to act as its servlet container, hosting the application code and managing all incoming HTTP requests. Internally, the application relies on the Spring framework to handle dependency injection, wire services together, and maintain database connection pools. Because IIQ is built on these standard Java frameworks, its performance constraints and scaling rules are ultimately governed by standard Tomcat HTTP thread pools and Spring context limitations. All of IIQ's operational state persists in a relational data tier. The schema contains over 200 tables, recognizable by their strict SPT prefix. This diagram shows the schema's center of gravity, the SPT identity table. A major challenge is storing unbounded custom attributes within a rigid SQL structure. IdentityIQ solves this by serializing attributes, like department and location, into an XML blob, stored in a single CLOB column. While this XML serialization provides infinite extensibility without requiring schema migrations, it makes raw SQL querying highly inefficient because the database has to parse text instead of reading columns. Because of this, engineers must always utilize the IIQ Java Object API rather than direct database queries to access these nested attributes. This brings us to the concept of the identity cube, a term used frequently in IIQ that does not actually exist as a physical database table. This visual represents the identity cube. It's a read-time aggregation built programmatically in memory. The conceptual cube forms by linking one central SPT identity record to many downstream SPT link records, representing the user's specific accounts in systems like Active Directory and SAP. This dynamic linkage allows IIQ to maintain strict relational database integrity while handling the messy, infinite variations of real-world enterprise identity data. To build those links, IIQ uses an engine called aggregation. This is a read-heavy process responsible for pulling the external world's current state into the platform. The read process initiates when the embedded task scheduler picks up a scheduled aggregation task. The scheduler then allocates a specific execution thread from the internal task executor pool. Using that thread, a connector authenticates to the target system and extracts the raw account data. This flow diagram shows the connector packaging that raw extracted data into a standardized format called a resource object. The critical operational pivot in this read path occurs here at the correlation rule. This custom bean shell script evaluates attributes, like an employee ID, hunting for a matching owner in the IIQ database. A successful match creates a direct database link, transforming the resource object into an SPT link connected to the core identity. This new database link immediately triggers an identity refresh process to recalculate risk scores and evaluate role policies based on the newly imported data. Aggregation functions as a continuous, programmatic reconciliation of external reality against internal access policy state. The counterpart to aggregation is provisioning. This is the write-heavy engine that pushes IIQ's desired state out into the external world. This document represents a provisioning plan. All write operations are strictly governed by this required data structure, which details specific creation attributes in an account request. When a user initiates an access request via the UI REST API, it immediately triggers the workflow engine to process that plan. This presents an architectural problem. Human approvals take days. If Tomcat threads waited for managers, the thread pools would instantly exhaust. To solve this, the workflow engine creates a work item for the assigned approver. The engine then completely suspends the active execution thread. Look at this thread process. To survive an indefinite pause, the workflow state is serialized and saved into a database row called SPT workflow case. Once approved, the workflow is deserialized. A new thread picks it up, resuming execution from the exact point it paused. The resumed workflow hands the plan to the provisioner engine, which partitions the operations by target application and executes them via connectors. This stateful database serialization is the only way IIQ can maintain reliable, long-running human-in-the-loop processes without crashing the Java application server. This execution model allows the system to achieve enterprise horizontal scalability. A load balancer routes incoming traffic to 3 parallel Tomcat IIQ nodes. These multiple independent Tomcat nodes all read from and write to a single shared database environment. The load balancer uses session affinity to ensure UI users stay connected to their specific Tomcat node during a session. Background tasks, however, do not rely on the external load balancer. Instead, they are coordinated internally via Quartz clustering. Database-level locking guarantees 2 nodes never execute the same background task simultaneously. Consider a critical node failure. If Node 1 crashes during a workflow, its serialized state is safely stored in the shared database, ready to be picked up and resumed by Node 2. IdentityIQ's ability to scale horizontally and survive hardware failures is entirely dependent on its design pattern of pushing state persistence down to the shared database layer. The entire platform rests on 3 core pillars: Java object models, XML CLOP serialization, and asynchronous stateful threats. Whether an engineer is writing a custom correlation rule or partitioning a massive Active Directory aggregation, this fundamental execution model remains identical. Ultimately, maintaining IdentityIQ at scale requires managing it not simply as software, but as a precise, highly tuned